This is Professor Ann Orion Spehar from the University of Alaska Southeast, and this is Part 2 of Economic Growth 1, the Solow Model, Savings, Investment, and the Golden Rule. In Part 2, we will learn how a country's standard of living depends on its savings rate, and we will apply the use of the Golden Rule to the growth model to determine the optimal savings rate and capital stock. We will then describe the transition process of moving the economy to the Golden Rule steady state using policies that impact the savings rate. Before we begin, let's consider our learning outcomes. After the student has completed this lecture, they will be able to explain how a country's standard of living depends on its savings rate. Apply the use of the Golden Rule to the growth model to determine the optimal savings rate and capital stock. And describe the transition process of moving the economy to the Golden Rule steady state. Continuing with the Solow growth model, let's ask now what impact does increased savings have on the growth of the economy and on the steady state level of capital and output. An increase in the savings rate S implies that the amount of investment for a given level of capital stock is higher. This means that the savings function is shifted upward. At the initial steady state K star, investment now exceeds depreciation, and the capital stock begins to rise again until the economy reaches a new steady state, where depreciation and investment are again equal. A new K-star is attained with a higher level of capital stock employed as well as more output. Note that the converse is also true. A fall in savings S, caused for example by tax cuts or government spending increases, leads ultimately to a lower standard of living. In the classic static model, we learned that a fiscal expansion crowds out investment. The Solow model allows us to see the long-run dynamic effects of crowding out investment. The fiscal expansion, by reducing the savings rate, reduces investment. If we were initially in a steady state, in which investment just covers depreciation, then the fall in investment will cause capital per worker, labor productivity, and income per capita to fall toward a new, lower steady state. If we were initially below a steady state, then the fiscal expansion causes capital per worker and productivity to grow more slowly and reduces their ultimate steady state values. This, of course, is relevant because actual U.S. public savings has fallen sharply since 2001. Here are the dynamics of an increase in the savings rate. An increase in the savings rate raises investment, causing the entire investment function to shift upward, causing K to grow toward a new steady state. Now let's see what the model says about the relationship between a country's savings rate and its standard of living, income per capita, in the long run or in the steady state. The Solow model predicts that countries with higher rates of savings and investment will have higher levels of capital and income per worker in the long run. But are the data consistent with this prediction? This scatter plot shows the experience of 96 countries, each represented by a single point. The horizontal axis shows the country's rate of investment, and the vertical axis shows the country's income per person. High investment is associated with high income per person, just as the Solow model predicts. The source for this table is the Penn World Table version 7.0, Center for International Comparisons of Production, Income, and Prices at the University of Pennsylvania, May 2011. It was produced by Heston, Summers, and Atna. In the Solow model, savings plays a very important role. In fact, we learned that as an exogenous variable, it determines the level of investment in each period and also allows for a higher level of capital stock employed and a higher level of output as well. So an economy can not only grow faster, but it can reach a higher level of steady-state output. But if this is true, why not save everything and maximize the largest possible level of output and therefore income? Well, it likely would not be the most comfortable economy to live in, as everything would go toward growth and nothing would be left for consumption. Remember, savings implies sacrificing consumption in this model, as there is no credit creation taking place. So the question arises, is there an optimal level of savings and therefore an optimal level of capital accumulation that would produce a maximum of well-being or consumption? There are many possible steady states. What is the best steady state that has the highest possible consumption per person? We want that steady state that maximizes consumption. We want the steady state that maximizes C star. By finding that level of savings that will give the highest level of steady state capital per worker, or K star. The steady state value of K that maximizes consumption is called the golden rule of capital, and we denote this by K star gold. Different values of S lead to different steady states. How do we know which is the best steady state? Well, the best steady state has the highest possible consumption per person, C star, and this equals the quantity 1 minus S times F of K star. An increase in S leads to a higher level of K star and Y star, which raises C star in the long run. But at the same time, consumption's share of income, the quantity 1 minus S, is reduced, which lowers C star. So, how do we find the S and K star that maximizes C star? This amounts to finding the golden rule level of capital, the steady state value of K that maximizes consumption. To find it, we have to express C star in terms of K star. Well, C star, or steady state consumption, is equal to Y star minus I star, which is just equal to F of K star minus I star. But we know that this has to equal to F of K star minus delta K star because we're dealing with steady state values. Remember, in the steady state, investment has to equal depreciation. Because if it weren't equal, for example, if investment were greater than depreciation, well then we would be accumulating capital every year, and that accumulation would be saved and added to the following year. But at steady state, we know that the change in capital is exactly equal to 0. And that means that investment must exactly equal depreciation. So now we have a function that says that C star is equal to F of K star minus delta K star. And let's think about what that means. We want to maximize consumption at the steady state values. And what this means now is that F of K star, or output, has to be the furthest away that it can possibly be with the depreciation function. That is, we want the greatest distance between output and depreciation. Let's see what that means on a graph. Let's pause for a moment and study this graph, as it looks very familiar with previous graphs. Yet it is fundamentally different with the other Solow model diagrams, even though the curves look similar. On this graph, the horizontal axis measures K star and not K. So once we have found K star using the other graphs, we plot that K star on this graph to see where the economy's steady state is in relation to the golden rule capital stock. Remember we said that there are many steady states? Well, this graph plots all the possible steady states. So this means that at every point on the delta K star line, delta K star is equal to investment. Notice also on this graph, the curve plots the production function, or output, at every possible steady state capital per worker. It does not plot F of K, it plots f of k star. It plots output and not sf of k, the portion of the output that is saved. On the other diagram, the intersection of the two curves determined the steady state k star. But on this graph, the only thing determined by the intersection of the two curves is the level of capital where c star is equal to 0. And we certainly wouldn't want to be there. The intersection identifies that point where investment, which is equal to depreciation, is just equal to total output, and therefore there's no output that's left for consumption. Also, in this graph, there are no dynamics, as we are in a steady state at every possible point on the x-axis. So the economy is not in motion. In the other graph, the gap between the two curves determines the change in capital, and this change is added to the next period's capital stock and results in a growing economy. Now that we understand the graph, let's see what it tells us. First and foremost, at every point on the x-axis is a k star, or it identifies a steady state. So all the possible points are stable equilibriums. We are comparing steady states and asking which is the best one, the one that maximizes consumption. Well, there is only one where consumption is maximized. And where is this? Let's think about this. Here is K star gold. Here is Y star gold, and it's equal to F of K star gold. This is where investment is equal to depreciation. And this is consumption. Notice we've picked that K star gold where the distance between F of K star and the delta or depreciation function is maximized. This will provide us with the greatest amount of consumption possible. Consumption will be maximized where the distance between depreciation and output, the gap between the two graphs, are the greatest. Look where C star gold occurs. It occurs where the gap between capital, depreciation function, and the production function is greatest. This is called the golden rule steady state. If the capital stock steady state is below the golden rule steady state K star, then an increase in the capital stock is increasing output more than it is increasing depreciation, and so consumption is increasing. After the golden rule steady state, consumption is falling because depreciation is rising faster than output. Depreciation is increasing at a constant rate, but output is increasing at an increasing rate before the golden rule steady state and increasing at a decreasing rate after the golden rule steady state. This gap, or the golden rule steady state, will always occur where the slope of the depreciation line is just equal to the slope of the production function. But we know that the slope of the production function is the marginal product of capital. We learned this in part 1. And we know from algebra that the slope of delta K star is exactly equal to delta. I've provided this slide for students who have had calculus. Otherwise, you may skip this slide. But deriving the condition that the marginal product of capital is equal to delta is straightforward. The problem is to find the value of K star that maximizes the function C star is equal to F of K star minus delta K star. Well, we take the first derivative of that expression and set it equal to 0. So F prime of K star minus delta is equal to 0. This is where it's maximized. We know this. This is the first condition. And so this implies that F prime, which is the marginal product of capital, is just exactly equal to delta. So F prime K star is equal to the marginal product of capital, which equals the slope of the production function, and delta is equal to the slope of the steady state investment line. They must equal at the point where consumption, C star, is maximized. There are no endogenous forces that will move the economy toward the golden rule steady state, because savings is an exogenous variable. So, achieving the golden rule requires an active policy intervention that adjusts S savings. Remember, policymakers can affect the national savings rate. For example, changing national savings by changing government spending or taxes. You know, like the government could hold taxes constant overall, but change the structure of the tax system to provide more incentives for private savings. For example, a revenue-neutral shift from the income tax to the consumption tax. But what happens during the transition to the golden rule? Before we discuss the transition to the golden rule steady state, let's go through a numerical example of finding the golden rule steady state. Consider the policymaker choosing a steady state in the following economy. The production function is the same as in our earlier example. Y is equal to the square root of k, which is equal to k raised to the 1/2. Depreciation delta is again 10% of capital. Well, this implies that delta k is equal to 0.1 times k. Now, the policymaker chooses the savings rate S and thus the economy's steady state. But recall that in the steady state, delta k star is always equal to S times F of k star. Now, if I divide both sides of this equation by delta, and then divide both sides of this equation by F of k star, this implies that k star divided by F of k star is equal to S divided by delta. And this equation, once I plug in the necessary parameters and the function assigned in this problem, this equation becomes k star divided by the square root of k, which is equal to S divided by 0.1. And now I'm simply going to square both sides. So this implies that k star is equal to 100 times S raised to the second power. So equation 5 tells us that we now have an equation that allows the policymaker to choose a steady state by first deciding on its specific level of savings. Here is an alternative way of finding the golden rule steady state. Find the capital stock where the net marginal product of capital, MPK minus delta, is equal to 0. So we take the marginal product of capital minus delta, and in this case it is equal to 1 divided by 2 times the square root of k, minus 0.1. And this is equal to 0. If you look at the last column in the table on the next slide, you find where marginal product of capital minus delta is equal to 0. You can see that it occurs where S is equal to 0.5. And this is where k star is equal to 25. And also note that consumption is maximized at this level of savings. C star is equal to 2.5. So we look for where the marginal product of capital minus delta is equal to 0. And we see that it is equal to 0 where savings S is equal to 0.5. We can plug 0.5 into the equation 100s squared from equation 5 2 slides ago to get k star. But we can see on this table that k star is equal to 25. So we use these results to compute steady state capital stock for any savings rate. This table represents the calculation showing the steady states that result from the various savings rate in the economy. And we see that the higher the savings leads to a higher capital stock, which in turn leads to a higher output and higher depreciation. Steady state consumption, the difference between output and depreciation, first rises with higher savings rates and then declines. Consumption is highest when the savings is 0.5, and therefore a savings rate of 0.5 produces the golden rule steady state. Now let's discuss the transition to the golden rule steady state, as a policymaker changes the savings rate to move toward the golden rule steady state. And let's suppose that the economy is at a steady state with more capital than it would have at the Golden Rule level. Then policymakers would like to try to reduce the amount of savings in order to reduce the amount of capital stock. But this will mean a higher level of consumption. Now, before we begin, note that on the x-axis is time. We are plotting changes in y, c, and I over time. T0 is the time when savings changes. So let's let T0 represent the time period in which the savings rate is reduced by policymakers. Note that before T0 we are in a steady state, and this means that K, Y, C, and I are all constant over time. There is no capital accumulation occurring, and so all variables are constant. We are not moving, and capital accumulation has stopped. At T0, the change in the savings rate doesn't immediately change K, so Y doesn't change immediately. Remember, savings equals investment, so a fall in savings causes a fall in investment. But because income is split between savings and consumption, this means that a decrease in savings results in an increase in consumption. Savings has fallen, but Y has not yet changed. It has just been reallocated between savings and consumption. What was invested before T0 is now consumed. But after T0, in the previous steady state before T0, savings and investment were just enough to cover depreciation. Then, savings and investment were reduced at T0, so depreciation is now greater than investment, which causes K to begin to fall toward a new, lower steady state value. As K falls and settles on its new, lower steady state value, so will Y, C, and I, because each of them is a function of K. Even though C is falling, it doesn't fall all the way back to its initial value. Policymakers would be happy to make this change as it produces higher consumption at all points in time, after T0, relative to what consumption would have been if the savings rate had not been reduced. Now let's suppose that the economy is at a steady state with less capital than it would have at the Golden Rule level. Then policymakers would like to try to increase the amount of savings in order to increase the amount of capital stock, because this will mean a lower level of consumption. So to reach the Golden Rule, savings must be increased. Let's consider what happens. Before T0, in a steady state where K, Y, C, and I are all constant. At T0, the increase in S doesn't immediately change K, so Y doesn't change immediately. But the increase in savings causes investment to rise, because higher savings means higher investment, and consumption to fall, because we are saving more of our income and consuming less of it. After T0, now savings and investment exceeds depreciation, and so K starts rising toward a new, higher steady state value. The behavior of K causes the same behavior in Y, C, and I. Qualitatively the same, that is. Ultimately, consumption ends up at a higher steady state level, but initially, consumption falls. Therefore, if policymakers value the current generation's well-being more than that of future generations, they might be reluctant to adjust the savings rate to achieve the Golden Rule. Notice, though, that if they did increase S, an infinite number of future generations would benefit, which makes the sacrifice of the current generation seem a bit more acceptable, don't you think? And this concludes Part 2 on the lesson on economic growth, the Solow model, savings, investment, and the Golden Rule. In Part 3, we will expand the Solow model to include effects of population growth and determine how population growth affects the steady state. This is Professor Anne Orion Spehar from the University of Alaska Southeast.